We'll start our tutorial with the introduction sections of the nRF24L01 Plus product specification document and see the basics about this transceiver. Then we will have a quick flashback to one of our previous videos in which we showed how to make a transmitter-receiver setup with two Arduino microcontrollers. As an extension of this section, we will look at the sketches of the transmitter and the receiver, and by checking the functions in the RF24 library, we'll try to have an understanding of what is being done with these functions. We will then introduce our new project in which we replace the transmitter side's Arduino microcontroller with an MSP430, and we will discuss how to write the code. First approach would be to create an identical library for MSP430, which is too much effort, and I was also not sure if I could finish it by myself. At this point, a new idea came to my mind, which was hacking, or let's say reading the registers of the transmitter module, which were already configured by the Arduino in the initial project. I'll show you how I did that in the latest section. After obtaining the register settings from the previous step, we'll go deep in the product description document to better understand the transceiver and figure out how we will program it with our MSP430. Actually, all the steps can also be done by another microcontroller unit other than MSP430, since what we will use in the code will be all digital input and output. We will even create the SPI by software. In the final section, I will show you the details of the code for both transmitter and receiver, and I'll relate it with the product specification document as I explained. Now, let's not waste time and jump into the introduction section. Let's start with our PCB that hosts our transceiver module. If we zoom in, we can see that the model name, the production year, week, etc. can be seen. It's good to check if your model is a plus or not. Here we can see that it's nRF24L01 plus, and we can see that the year is 20 for 2020 and week is 12. In this key features section, we can see the air data rates. In our project, we will be using 1 megabit per second, but there are two other options like 250 kilobit per second and 2 megabit per second. For the device, we are going to be supplying 3.3 volts from the Arduino or the MSP430 launchpad. Also, it's important to mention that you can connect up to 6 transmitters to a receiver over 6 data pipes. Here we can see that we are going to use Serial Peripheral Interface, SPI, to control the transceiver. And as I said, for the MSP430 launchpad, I didn't use the hardware SPI, but I wrote my own software SPI, which is much easier to demonstrate. Also mentioned here the enhanced Shockburst engine, which takes care of the on-air communication and acknowledgements and retransmissions and etc. So you don't have to program this part of the communication with the microcontroller unit. In this page, we see the pins of the transceiver. Since we are using a PCB which has the necessary connections, we will only use the first 8 of them. Actually, in my code, I didn't use the IRQ pin. You can implement it if you would like by connecting it to your microcontroller and use ISRs, interrupt service routines. Instead, I checked the status register to set the actions for the transceiver module. In our first project, we had configured the nRF24 module as the transmitter with the Arduino. So this one was our transmitter. And on the other side, we had our receiver. This was our receiver module. The transmitter module was obtaining the outputs of the 7 MQ series gas sensors, and it was sending it to the receiver module constantly. So once we power on the device, all the 7 MQ sensors data will be sent to the receiver. So once we open the serial monitor on the receiver side, we can see the values flowing through the monitor. Now let's take a look at the transmitter and the receiver code for the Arduino Nano setup. You can see that we are including the SPI library, the nRF24L01, and also RF24 library. And we are initiating this instance by showing which pins are connected to C and CSN. Then we enter the address that we are going to use for the transmitter and also for the receiver. And then you can see that we are starting using the functions related to this library. So, for example, let's check the begin function. You can check the rf24.cpp file in this location, or you can go to the GitHub page, and in the GitHub page you can also check the same file. It's also present here. Okay, Now let's check this radio begin function. This is just actually a check of the CE and CSN pins. Actually, it's doing nothing much. Let's go back to the transmitter code, and then we use the open writing pipe function. Let's check that one. Okay, here we have it. Here you can see that it's writing to the register RX address P0 and also TX address. You are going to see in the document that these two addresses need to be the same. You can also check that information in the multi-receiver configuration as well. We will see those in the product documentation. Okay, so what it does basically is writes to the registers the value which is passed to it. And that value is the address that we had already defined earlier, okay? Now another function is set PA level. And let's see what it does. You can see that it writes to the RF setup register with the information provided to that. And you are going to see that in the documentation, we will have 4 PA levels. And here we are choosing PA minimum, which is going to correspond to -18 dBm. We will see that in the document, but now we can understand what it does. After that, again, we are at the transmitter side. We are using this stop listening function. Let's see what it does. Okay, it first sets the CE low, and then we have 100 microseconds of delay, and we power down, power up, and we again write to the register, enable RX address, and we enable RX on pipe 0, okay? And we use the child pipe enable 0, first element of this array, which is ARXP0. And after that, in the loop, these are related to the analog read of the MQ sensors. It's not related directly with the transmitter code. So we create our integer array here, and then we use the radio write function, okay? And we give the parameters data to send and also the size of data to send. So let's see what it does. Okay, actually it's very complicated, but generally we can see that we are writing some values to the status register, okay? And we will see when we look at the product documentation what these values are related with. And we can see that if maximum retry is exceeded, we flash TX, which is another instruction which clears the transmit FIFO. So this is related with transmitting the payload, okay? We are in the while one loop, so actually void loop in Arduino IDE sketch. So it's repeating itself. It's getting the updated values from the sensors. It creates the data to send array, and then it sends it to the receiver each time this loop is executed. So now let's look at the receiver side, what it does. Okay, so this is the receiver side. We again have this radio begin, again open reading pipe with the address. Again, we set the PA level to PA min, so these are all the same. This time we are starting listening instead of stop listening. Okay, so let's check this one. Okay, this is related with setting the device as a receiver. Actually, this primary RX bit in the config register is choosing between the transmitter and the receiver. Okay, so if it's 1, it's going to be receiver. If it's 0, it's going to be transmitter. So we will see this in detail when we look at the product description again. And then you can see that we write to the configuration register, and then we write to the status register. And then we set CE high. And when we set CE high, you will also see that in the product description, we activate the device. Either it's in the transmitter role or it's in the receiver role, okay? And in the transmitter role, we generally use a 10 microsecond pulse in the CE side so that we activate it as a transmitter. We will see those all in the product description. And this time we have an if clause here, and it says that if radio is available, perform these. So let's check what this available checks. This is also checking the status register, and you will see that we will do the same while configuring the MSP430. We will check if there is information in the receive FIFO. So if this clause is equal to 1, we are going to use the radio read function. And we again give these parameters because both at the transmitter side and the receiver side, we should know the structure of the data that we are receiving, okay? So let's check this read function. Okay, this is again a long one, but this is related with using the RX payload instruction. We will see that as well in the product description to read the receive FIFO and send it to the microcontroller. And as you can see, after we read that, we print it with the serial print function and we display it on serial monitor at the receiver side. So this is all about the Arduino code. Let's go to the next section now. So as you saw in the previous section, it's really hard to write a new library for the MSP430 from scratch. So I started thinking about a new solution, which was hacking the Arduino pre-configured nRF24 transmitter registers in the initial project. So I knew that this transmitter was running properly and the nRF24 registers were already configured. So if I could find a way to read those registers, I could implement that in the MSP430 as well. So what I did was to disconnect all the jumper cables from the already configured nRF24 module, except the VCC and the ground pins. And then I connected those jumper cables to the MSP430, and with the code that I've written in CCS, I was able to read all the registers values easily. Before we continue our tutorial, we should go to this website in order to download the documentation in nRF24 series L01 Plus product specification, and we click on the PDF. So this is the PDF that we will be following, so you need to download that. Now we'll go deep in the product specification document based on the information I provided until now. First thing we need to understand is the data and the control interface in the 8th section. So let's go to page 50 in the document. Here you can see that we will be dealing with 6 digital signals related with the data and control interface, and 4 of them are related with the SPI. So these are the SPI inputs and outputs. As I mentioned earlier, we will not be dealing with the IRQ pin, but you can implement your code accordingly if you want to use ISRs with the IRQs. And the other pin is CE, so this is active high and is used to activate the chip in the RX or TX mode. Let's first see how we are going to define these pins, either inputs or outputs, in the microcontroller side. So let's say that this is our MSP430. So CE is going to be output. CSN is going to be again output. Clock signal is again going to be output. Master out slave in, as its name implies, it's going to be master output. However, master in slave out will be input because this is going to be an input towards our microcontroller. As I mentioned earlier, you can use any microcontroller other than MSP430. And this is an important sentence. You can see that you can use 1-byte SPI commands, which we are going to see in the coming sections. You can activate our nRF24 module, data FIFOs, or the register map during all modes of operation. Here we see that the SPI is a standard SPI with a maximum data rate of 10 megabit per second. As I mentioned earlier, I'm going to be using my own software SPI, meaning that I will be writing each code for the clock, for the CSN, for the CE, and etc. Also for the master in slave out, master out slave in. Since our default frequency in the MSP430 is 1 megahertz, we will not be having a problem complying with the standard. Looking at the SPI commands, this is a very important section. So for example, this status register is serially shifted out on the master in slave out pin simultaneously to the SPI command word shifting to the master out slave in pin. You will see these in the diagrams as well. So we will stick to this diagram and understand each part of it. So about the command word, you can see that the most significant bit starting first and then ending at the least significant bits. Okay, so this is going to be our command word. And data bytes, if we are going to handle more than 1 byte, the first one will be the least significant byte and the last one will be the most significant byte. Okay, and in each byte we are going to be sending the most significant bit first. We will see this in detail in the diagram. This is maybe one of the most important tables in the document. Here we have a list of all the commands that you can send to our nRF24L01 Plus module, and we will be using some of them very often. So let's go through them. For example, this one is the read register command, and its binary representation is like this. Okay, so we will have 3 zeros in the most significant bit part, and 5 bits will change according to the register that we would like to read at this time. Okay, so maybe it's better to name these X instead of A, because A reminds me of the hexadecimal number 10. However, this doesn't mean that, so this is binary. Okay, let's state this once again. You can read a single register which is consisted of 1 byte or up to 5 bytes. Okay, so if you are reading more than 1 byte, again you are going to be reading the least significant byte first. Actually, the write register is very similar, but you can see that the command starts with 001 instead of 000, and you can write 1 or up to 5 bytes with this command. And here this AAAAA is equal to the 5-bit register map address. We are going to go through all the register addresses and see how they work. This one is read RX payload, which we are going to be using in the receiver module. Okay, so this 8 bits correspond to read RX payload. And you can read up to 32 bytes, and again we are going to be reading the least significant byte first. One important thing, as mentioned here, payload is deleted from FIFO after it is read. Okay, and this is used in RX mode. And the next one is write transmit payload, and this is the 8 bits of it. Again, we are going to be sending up to 32 bytes. This time we are sending, and we are going to be sending the least significant byte first. 2 flash commands, one for transmit FIFO, one for receive FIFO. So these are the codes for these commands. And we don't send any data bytes. As you can see, these are single instructions. We send it, we don't read anything after that, we don't write anything after that. Okay, so this is used in transmit mode, this is used in receive mode. Here we have the reuse transmit payload. It reuses the last transmitted payload. These 3 commands, I won't be using them in my code, but you can go into the details of them if you would like to understand those. However, I'll be using the NOP command, actually, which does nothing, but it is used to read the status register. You'll see that in each command that we send, let it be NOP or flash or read, write, as we send the command byte, at the same time we see the status register from the device. You will see it in the diagram as well. So now let's see the SPI timing and how SPI works. Actually, this document is also very useful if you'd like to understand how SPI works. So let's see that. Okay, here we have CN stands for SPI command bit, C for command, SN status register bit, DN data bit. Okay, so this one is the read operation. Okay, and this one is the write operation. Let's see how we are going to implement the SPI in software. Okay, So you can see that we have the 4 wires or 4 pins that we are using for SPI. Okay, so this is CSN, this is clock, this is master out slave in, and this is master in slave out. Let's look at this from a different angle. Okay, so because I'm going to divide it into pieces. So this first piece is going to be this part. And I'm going to make a function that performs this section. Okay, this is sending the command byte. It will be the same for both read and write. You can see that it's the same. We can show it here as well. It's the same for both read and write. So let's see what we do in this section while we are sending the command. First, we set CSN low. Okay, so we should have a simple function that makes CSN high or CSN low. And we will have a clock function which is going to send a clock pulse, which is actually setting it 1 and then setting it to 0. Okay, we will do it each time we would like to send a bit or read a bit. And as indicated in the document, whenever we send the command, this is the command byte starting from C7. Why starting from C7? Because we send the most significant bit first, as implied in the document. As we send the command byte, we receive the status register at the same time. So in our instruction byte, we should have a function that reads the master in slave out pin and sets it to the status register. So each time we send the command, we will read the status register. Okay, let's continue with the read operation. Let's assume that we've done this function and we sent our instruction. What is next? So since we are reading, we will be continuing to get data from the master in slave out pin. Okay, so each time we send a clock pulse, nRF module, which is right here, okay, at this side, nRF module is going to send some data. It's depending on which function we sent. Okay, for example, we wanted to read a certain register, okay, maybe config register, and it's going to send us 1 byte at that time because config register is consisted of only 1 byte. However, if we are accessing a multiple byte register up to 5 bytes, then it's going to first send the least significant byte, okay, as you can see here, continuing to the most significant byte. However, we are going to receive the most significant bit in each byte first. As you can see, D7 here, okay, D15 here, and etc. This means that for the read operation, okay, what we are going to do is set, let's say, first set CSN low, okay, and we start to send our bits for the command byte, send bits for command byte, read master in slave out for status register, and we will send clock pulse. So actually this is going to be our instruction. And after sending this instruction, we will still keep the CSN low because we are going to be reading some bytes here. Then we will be getting the most significant bit for the read operation, and we are going to shift it to the left in each time we send the clock pulse. Okay, assume that I received the D7 bit first. Next time in the next clock cycle, I need to shift it to left in order to receive D6, and after 7 steps, after 7 shifts, let's say, what I will get is D7, D6, D5, and down to D0, okay? I need to make this shift operation because I'm receiving the most significant bit first. And if I'm receiving a multiple byte, then I should have some kind of an array to store this. Okay, if we continue with the write operation, The first section is identical to the read because we are going to be sending a command. But this time it's going to be writing a register. And after sending the instruction byte, we will continue sending bits to our nRF module. So this time we will be sending bits, not receiving bits, but sending bits towards the master out slave in pin, starting from the most significant bit and ending at the least significant bit. And starting with the least significant byte, ending at the most significant byte. So you will see the details of these instructions in our code, and I believe you can easily relate this tutorial section with the code. Now let's skip the timing details and let's jump to page 55 to see the data FIFO. TX3 level 32 bytes FIFO, RX the same. So this is receive FIFO, this is transmit FIFO. Accessing the FIFOs is done with these commands. So let's highlight this section. You can write to the TX FIFO, write to the TX FIFO with write TX payload, write TX payload with no acknowledgement, and write acknowledgement payload in PRX mode. Okay, so 3 commands that can be used to access the transmit FIFO. However, the receive FIFO can be read by this single command, read RX payload. Okay, about the interrupt, as I said, I'm not using the interrupt. However, you can use it and you can use ISRs. There are 3 interrupt sources. These are TXDS, RxDR, and MaxRT. So let's go quickly to the status register in order to understand what these mean. Let's go to status register, which has the address of 07 hexadecimal. And you can see that RxDR is data ready RX FIFO interrupt. TXDS is data sent transmit FIFO interrupt, and MaxRT is maximum number of retransmits interrupt. Each time these things occur, we receive these interrupts from the IRQ pin. However, you can mask these interrupts from the config register. You can mask these by setting these bits 1. Even though we will not be using interrupts, we will be using this status register, and we will check the values of these bits and we will act accordingly. For example, while in the receiver mode, we are going to check this RxDR bit, and if it's 1, we will understand that there is new data ready to be read, and we start reading. For example, if we receive this MaxRT interrupt in the status register, we understand that maximum retransmits has occurred, and we need to clear this bit, otherwise the communication will not continue. Okay, this was about the interrupt section. Let's go back to the register map and continue from the first register, which is the config register, okay? And its address is 00. So for example, if you would like to write to the config register, let's have a quick understanding of it. The hexadecimal address is 00. So if you would like to write to the config register, what are we going to do? Let's go to the command. Okay, we would like to write to the config register. So what we are going to send is 001, and since the address of the config register is 0, we will add 5 zeros. Okay, so this is the command that we are going to send to write to config register. What we have to send is, so let's clear this section. What do we have to send? 001, 0, 0, 0, 0, and 0. So this is for writing to the config register. After we send this, we need to send the 8 bits that we would like to set. So this will be the config register as we want it. Assume that we would like to disable all these interrupts. We have to set these all to 1, right? So the most significant bit is reserved, so it's allowed only 0. We will have 1, 1, and 1 here. And this one is enable CRC. We will be enabling CRC. So we will have 1 here, CRC encoding. We will be having 2 bytes of CRC encoding in our example, so it will be 1 again. Power up, power down is depending on where you are in the code, because we would like to configure our device and then power it up at the end of this configuration. Okay, so first let's have it as power down, and in another write config register command at the end of the configuration, we will send a power up. Okay, and this is one of the most important bits, primary RX. If you would like to set it as transmitter, we are going to have it as 0. If we are going to have it as receiver, we are going to set it as 1. Let's assume that we are going to set it as transmitter. So what will be our config byte? So this is 0, 1, 1, 1, 1, 1, and zeros. So this is what we need to send to the nRF module. This was 0, right? And actually I cannot recall very well, but it should be all 5 ones to be sent. And we won't have this rest because we are only sending 1 byte. And what we are going to do at the end is we are going to set CSN high. We set CSN low in the beginning, sent our command byte, and then sent the values for the config register, and we set again the CSN high, and we are finished. We have written this following values to the config register. So this was a quick example. So let's continue with the details of the register map. We saw what the config register is all about. As I said, the most important bits maybe here are primary RX, power up. These are also important bits. The next register is enable auto acknowledge, which is related with enhanced Shockburst, and we are using it. So if you would like to enable auto acknowledgement function, you need to set the pipes value to 1. Okay, you can see that we have 6 pipes. Okay, data pipe 0 up to data pipe 5. So if you would like to enable auto acknowledgement, we set these as 1, and by default it's all 1. So this is the reset value. So you can set it or you can leave it to reset, so it will be already 1. So enabling RX address, so this is enable RX address register. So if you would like to have data from different data pipes, you can enable these. Okay, by default only data pipe 0 and data pipe 1 are enabled, and this is actually enough in the first configuration. Setup of address width, so we are going to be using 5 bytes, and by default it's already 5 bytes. You can see that 11 stands for 5 byte address width. The next register is setup of automatic retransmission. We already configured this in our example as well. So these are the values and you can relate it. So in each step you are adding 250 microseconds of extra delay. And this is the retransmit count. So you can have up to 15 retransmits. If you don't receive an auto acknowledgement, you can retransmit up to 15 times. Next register is the RF channel. You need to have the same value in both the transmitter side and the receiver side. In the RF setup register, you are setting the on-air data rate. So as I said earlier, we will be using 1 megabit per second. So we will have 0, 0, 0 at DR low and DR high. So this means that we will have 0 here and we will have 0 here as well. If you would like to set it to other values, just map these with the register values. Okay, this you should be remembering. This one is the RF power. Remember the PA min value in the Arduino code. So that PA min stands for 00, which stands for minus 18 dBm. Okay, so we are going to be having 00 in the 1 and 2 bits of the register RF setup. Okay, we saw what status register was, actually a part of it. So each time we send a command, we receive the status register at that time, okay? So these are related with the FIFOs, RX FIFO, TX FIFO, maximum number of transmits, interrupt. And this one is another important 3-bit information, which gives the data pipe number. So assume that you can have up to 6 transmitters, and all those 6 pipes should be distinguished from one another, right? So this stands for 000101 is in decimals 0 between 5. So this is 6 pipes. Meaning that at some point, if you read, for example, in these 3 bits 010, means that what you have in the RX FIFO at that time is related with data pipe 2. So what you received was from data pipe 2. And the least significant bit is the TX full bit. It indicates that transmit FIFO is full if it's 1. And the next register is observe TX transmit observe register. It counts lost packets, counts retransmit packets. If you would like to get some statistics, you can read these registers. Receive power detector. This was called carrier detect in the non-plus version. And if we continue with the RX address P0 to P5, you can see that these are the receive address of data pipe 0, data pipe 1, 2, and etc. But there is something different in the structure of it. Data pipe 0 and data pipe 1 are consisted of 5 bytes, okay? So you can see that this is 40 bits. Again, this is 40 bits. However, the others, P2, P3, P4, P5, are only 1 bytes. In P2, P3, P4, and P5, the most significant parts are the same, meaning that it's going to be C2, 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 and C3 for P2, C4 for P3, and etc. But you can change it if you would like. And again, meaning that if you'd like to write to the P0, then you need to send 5 bytes. Also for P1, again 5 bytes. But you don't need to send 5 bytes, you need to only send the least significant byte for the other addresses. And the TX address register is the transmit address. It's used for a PTX device only. However, I used it in the receiver code as well. It doesn't hurt. Again, a 5 bytes address. And this is default value. We are changing it to 0001. You may remember it from the Arduino code as well. The next one is RX payload width P0. This means that we are setting the payload width for the pipes. So here I'm saying that, for example, if I'm writing here 32 in decimals, okay, I've got 6 bits here. So if I write 32, means that I'm expecting 32 bytes of data from this pipe. I'm setting the payload width for this pipe. Same for the others, pipe 1, pipe 2, pipe 3, pipe 4, pipe 5. And for the FIFO status register, actually I'm not using the FIFO status in my code as well, but you can implement it. You can do actions on the value of this FIFO. Actually, this 1C and this 1D, I did not implement them in my header file because I had started with the non-plus version. But since I didn't use these registers, because I don't use the dynamic payload width, I'm using a static payload width, I didn't deal with these registers, but you can read them and you can implement them if you would like. And the feature register, you can see that we have here enable dynamic payload length. So if you have set the previous register, you need to enable dynamic payload length as well here. So you need to set it to 1. So this one enables payload with acknowledgement, enables the write transmit payload with no acknowledge command, which I didn't use, so I didn't deal with it either. Now let's continue with the radio control section, which is the 6th section in the document. There are 4 different operational modes, which is power down, standby, receive, or transmit. And we are going to continue with the state diagram, which is very useful in order to build your algorithm in terms of the receiver or the transmitter. You can see that there are distinct states: recommended operating mode, possible operating mode, transition state. So this diagram is very useful. Let's zoom to it a bit. You can follow these bold arrows in order to find the recommended path between operating modes. So once we power up, or let's say supply the device with more than 1.9 volts, we are going to have a power on reset of 100 milliseconds, and then we will be in the power down state. And then once we have this power up is equal to 1, by the way, just check that this is the bit state condition, okay? So remember that this was in the config register, so we need to update the config register. We need to write to the config register to set this power up bit. Then we are in the transition state and then go to standby 1 state. And once we are in standby 1 state, we can go to the transmit mode, which needs the TX FIFO as not empty, and primary RX. Remember, primary RX was in the config register as well. And once we set it to 0, we set the device as transmitter. And if we have CE, which is the pin signal condition, is equal to 1 for more than 10 microseconds, then we will be in this transition state again for 130 microseconds, and then we will be going to the transmit mode. And as long as we have the chip enable is equal to 1 and transmit FIFO is not empty, we are going to be having a loop in the transmit mode. And you can follow the other paths as well. So if we have power up is equal to 0, then we go back to the power down state. If we have C is equal to 1, however the TX FIFO is empty, then we go to the standby 2 state. And let's check the receiver state. For example, we were in the standby 1 state, then we had the primary RX as 1 and C is equal to 1, which is the same condition in our receiver code. Please go and check it. Then again, we are going to be having a 130 microseconds of settling transition state, and then we go immediately to RX mode. These two modes are our expected modes, okay? One's in the receiver side and this one is in the transmit side. So if we continue with the modes, actually I'll be skipping this power down standby modes. You can check them if you would like. Let's quickly go to the RX and TX mode, which are actually important for us, RX mode and TX mode. So once we have the power up bit and the primary RX bit and the CE pin set as high, then we enter the RX mode. Primary RX, when it's equal to 1, then we are in RX state. On the other hand, just jump to the TX mode and see that primary RX, if it's set to low, if it's set to 0, then we will be in TX mode, okay? And in the TX mode, again, we have to have the power up bit set high, primary RX bit set as low, and we need some payload in the transmit FIFO. And we need a high pulse on the C for more than 10 microseconds. So if this is our C signal, we have a pulse which is, this duration is 10 microseconds minimum. Okay, this table is also a very important table, so you need to make sure that you understand these 5 modes, and with power down it's 6 modes. So RX mode, both these are TX mode, standby 2, standby 1, power down. So this is the power up registers value. This one is in the config register. This one, primary RX register, is also in the config register, and C pin is the pin that we are controlling with our microcontroller. So once the power up register is 1, primary RX register bit is 1, and C input pin is 1, then we are in receive mode. We are in transmit mode in both sequences. 101 and 10 minimum 10 microseconds high pulse. And this is our standby 2 state, and we need to have the TX FIFO empty, and standby 1 state and power down state. And you need to comply with the timing informations. Remember that in our diagram we had some transition states. Okay, for example, once we set the primary RX as equal to 0, C pulse, transmit FIFO not empty, we will have 130 microseconds of transition state. So in this state, we should not be sending any commands from the microcontroller in order to comply with the timing information. Okay, same applies with the RX setting as well. And remember that we had this power on reset 100 milliseconds. So at this point, we should not send commands to the nRF module as well. And air data rate, we had mentioned this early in this tutorial. It can be 250 kilobits per second, 1 megabit per second, or 2 megabits per second. And it's set by the RF_DR data rate in the RF setup register. We had gone through the registers as well. And this is very important. Let me highlight it in red. And transmitter and the receiver must be programmed with the same air data rate to communicate with each other. So if you have 1 megabit per second on the receiver side, you should have the same in the transmit side as well. And you have to use the same RF channel frequency as well. You can see it here. Let's highlight this too. You must program a transmitter and the receiver with the same RF channel frequency to communicate with each other. And PA control, remember this. We had mentioned it a couple of times through this tutorial. Remember that if we had it 00, that would be the minus 18 dBm, and this was the PA_min, I guess, if I'm not wrong, in the Arduino code. This section also says that RxTX control is set by the primary RX bit in the config register, which is a very important bit. About enhanced Shockburst, I won't be going into the detail because this is a very good feature and you don't have to deal with the on-air transmission, retransmissions, or any other thing. Both nRF modules at the receiver side and the transmit side are handling it. However, if you would like to go into the details, you can see how it works. You can see that 1 to 32 bytes of dynamic payload length. We are not using dynamic payload length, but you can use it if you would like. 6 data byte multiceiver for star networks. Maybe at this point we should go to this multiceiver. Okay, this is describing the multiceiver 7.6. So you can connect up to 6 transmitters to one receiver having 6 data pipes. Data pipes will be between data pipe 0 and data pipe 5. Okay, 6 data pipes. Remember in the registers I had mentioned that data pipe 0 and data pipe 1, these have 5 bytes of address, and data pipe 2 to data pipe 5 have these 4 bytes, same, and the least significant byte changes. So you just write 1 byte to data pipe 2, 3, 4, and 5. And this one is also a nice diagram. So if you are using this multiceiver property, for example, in your data pipe 0 and at your transmitter 6, you need to have the same address both at the transmitter address and RX address P0. Same for the data pipe 5, 4. The addresses should be the same at the transmitter side, and in the receiver side, you should have 6 data pipes for sure, and these should be complying with the addresses that are given at the transmitter side as well. So this data pipe 1 is this one, data pipe 2 is this one, and etc. So as I said, I will be skipping the enhanced Shockburst side, but if you would like to see the packet of it, if you would like to see what the preamble is, what the packet control field is, you can go through these documents. cyclic redundancy check, we also showed that we are setting if there is 1 byte or 2 bytes in the config register again. And these diagrams show the automatic packet assembly. If you want to go into details, you can check these as well. And this one is the disassembly, auto acknowledgement, auto retransmission. And you can check these flowcharts for the transmitter operation and the receiver operation. You can see that this whole diagram is for the enhanced Shockburst. This dashed part is the Shockburst only. Same applies for the PRX operation. And we had gone through the multiceiver already. Okay, after going deep in the product description, now let's check how we read all those registers with a single file. And by the way, I would like to mention the header files that I have created. These header files are actually nothing but giving the instruction codes. Remember the command codes. So this one was for read registers, this one was for write registers. And you will see how I'm going to use them. And these are the register addresses. And in this plus header, which I didn't use in the example codes, since I'm not using these commands and also these register addresses, I didn't have this nRF24Plus.h. I just added it as a new header file. This one is sufficient. And you can see all the register addresses listed in this header file. So if we check this main.c file, which reads all of the registers on an Arduino configured transmitter device, remember that I was mentioning about hacking the device, reading all those registers. This is how I do it. So I define all of these registers. If they are single bytes, I just use 1 as an index for those arrays. And after that list, you can see that I'm defining the S-clock pulse, send bit, CE on, CE off, CSN on, CSN off, and instruction byte MSB first, read byte MSB first, write byte MSB first, write payload MSB first. And what I do in this code is just send the instruction byte and say that read register, and I make an OR operation with the config. Just go back to the header file. You see that what I do is just read register, so I get this command, and with whatever register that I would like to read, I end it with this one. So in the end, I give this instruction byte reading the config register, and then I give the read byte MSB first, which says that you are going to read only 1 byte, and write it to the read register config. I use this structure, read register, enable auto acknowledgement, read register, enable RX address, etc. Remember that we were setting the CSN low before we sent the instruction or command byte, and then we were reading or writing the necessary content, and then we were setting the CSN on again in order to finish this command read or write cycle. Okay, I do it for all the other registers as well and save them in their related arrays. And after running it, I will be able to see those values in the expressions window. You can see that I've added all of these read register values. And let's go quickly to those functions as well, which I use in all of the codes. This one is clock pulse. It's very simply setting the clock high and then low, okay, with these 2 lines of code. This one is the send bit function. If you go in details of the instruction byte, you'll see this send bit function. So I'm sending the byte bit by bit, okay? So when I'm sending a command or I'm writing to a register, I use this function inside these functions. So what it does is, if the value that it gets at that particular bit of a byte, if that's not equal to 0, it sends out 1. Otherwise, it sends 0. It's as simple as that. And this one, CE on, is just setting high the CE bit, CE off setting low the CE bit, CSN on and CSN off same as C on C off. However, the pin has changed only. So I'm not using this write byte function because I would like to write the MSB first. And this one is the instruction byte MSB first. Why is it different than the write byte MSB first? Because remember that while we were sending the instruction byte, at the same time we were reading the status register. So it includes that section as well. So it sends that 8 bits of command by this code, and at each clock cycle it reads the status register and it's shifted left. Remember how I did that? Because I was receiving the most significant bit first and I'm shifting it to the left. So after 7 steps I'm getting the exact status register, okay? And at the end I send a clock pulse. We had described this in the previous section. And this one is the read byte MSB first. So after I send this instruction byte, which for example is a read register byte, this one checks first how many bytes it's going to read. Okay, so this first parameter is how many bytes we are going to read. Okay, so this is the first for loop for that. And then it reads the values from the master in slave out pin, bit by bit. Okay, and it sets the related register name and shifts it to the left in this loop. So what I get is whatever I sent as a register name is going to include the register's values that I would like to read. This one is the write byte MSB first. This one is for sending the byte. After I read all these registers, I had values in this expressions window, and I just copied those and pasted in an Excel file. So let's check that one. Okay, so this was the values from the nRF module, which I had configured it with MSB430 as a trial. Okay, so these values are not the values that I would like to reach. And this one, this column, the E column, is the hacked or read registers which were configured by the Arduino. Okay, so these are the register values that I would like to reach with the MSB430 as well. So let's compare these two sides. For example, this config register that was configured by the Arduino microcontroller says that we are going to be using CRC as 2 bytes, and it says the power will be on. You can directly check it from the document and you will see that primary IX bit is also 0. This means that we have configured it as transmitter. Okay, enable auto acknowledgement. This is the values that I would like to reach. Enable RX address, FIFO status. This one is observe TX, which is read only, so no problem with it. I just highlighted the ones that I needed to change with the red color. And for example, the RF channel was set to this one by the Arduino controlled device. RF setup, you can see that RF setup is also different, which says that the data rate is 1 megabit per second and PA is equal to PA min, so that's minus 18 dBm. RX address P0 has to be 00001. So these are ASCII characters. So these are the ASCII characters representation in binary. So don't get confused. These are the RX addresses. Actually, we will not be using 1 to 5, so that doesn't mean anything. And in the beginning, I had thought that these values were the same, so I didn't change the RX payload with P0 values. However, you need to check it carefully since this one was 0. However, this one is 32 bytes. Actually, I had big problems since I did not update these because the payload that the receiver was expecting was 32 bytes. However, I was not setting it, so the device was not working. So you need to check this one as well. For our code, only pipe 0 is sufficient because we are having only one transmitter and one receiver. This one is the setup of retransmissions. You remember that the first part was the delays, these 4 bits, and the other 4 bits were the retransmission numbers, so it was up to 15. And this was the transmit address 0001 as well. So by reading all these registers, I wrote those same values to a device that I controlled with the MSP430, and it worked perfectly. Now we are about to reach the end of our tutorial. We are going to see the transmitter and the receiver. You are going to see that this one is going to be our transmitter, MSP430, as controlling the transmitter module, nRF24L01 plus. And on the other side, we have our RX. In this slide, I will be only focusing on the TX side. And now let's see how I'm configuring the device. You can see that I'm writing to several registers. We had already mentioned those. This is auto acknowledgement, RF setup, and etc. And at the end, I write to the config register. This one, we can call it as the config section of our code. And then I start to write the payload. Since I had configured the payload width as 32 bytes, I'm sending a payload of 32 bytes. And then what I'm doing is setting the CE on and then having a certain delay and CE off. This is my CE pulse, okay? Remember that I had to send a pulse at a minimum duration of 10 microseconds. This is what I do there. So after I do this, my payload is transmitted towards the RX side, and I need to set a certain delay to justify auto retransmit settings. But remember, I was using 15 maximum retransmits, and I was having some delays in between these retransmits. Assuming the worst case scenario, I should set a delay that satisfies this duration, okay? So that I don't send any other command to the nRF24 module in this meantime. Then what I do is I receive an acknowledgement from the receiver side, hopefully, and this is the enhanced Shockburst side of the communication. Then what I do is I send a knob. This is only for reading the status register. And why am I reading the status register? To see if maximum retransmissions is equal to 1 in the status register. Because if that's the case, I need to clear that bit. So that's what I do, clear status register. And I also flush the transmit FIFO. And I do this in a loop. So this is my while one loop in CCS code. So you can go to the links that I provided for the CCS code for transmitter, and you can directly map this algorithm with the code. Now let's jump to the receiver configuration. So this time I have Arduino and nRF24L01 plus at the transmitter side, and I'm going to focusing on the RX side this time, which is again configured by MSP430. What I do is again write registers. Actually, most of the things are nearly the same. However, remember that I need to set the nRF module as a receiver, so my config register is going to be different for sure. The least significant bit is going to be 1. After I do this, this is my config part. I set the CE as on. So this makes the device start as a receiver. And then I send a knob to read the status register. And if there is data in the receive payload, so this is checking it, RX underscore DR is equal to 1. Then what I do is I set CE off, read the payload, and then clear the status register. Then I have the enhanced Shockburst. I had the transmitter transmitting payloads. My receiver sent the acknowledgement. I repeat this in a loop in order to read all the transmitted payloads. So you can also relate this algorithm with the receiver code that I had provided in GitHub. You can find all the links in the video description.